today we'll have Brett Nasserden, who will tell us or give us an introduction to Borel-Weil-Bott.
Hello.
Oh, do you have the mic?
Should I?
Yeah, you need the mic for the.
Oh, perfect.
All right, give us a second while Brett sets up the mic.
Yeah.
Brett.
Hello, can you hear me? Okay. I guess what's the question, like who here is in Borel-Weil-Bott? I know it's changed Sasha's life. Changed its former boss's life. Okay, I guess maybe I'll just say the plan. I do it from a maybe from a conceptual standpoint. That can cover different examples. One, and then two, what are we gonna do? And so I think the main case is on the flag variety, G mod B. So here G and N. Of our triangular matrices, and then use go to partial flag varieties. Draw some monuments, and then we'll maybe do some application. So this is the rough plan. So we'll start with X. This will be smooth, projective over C. Everything is going to be in characteristic 0. And I'll start with a vector bundle of rank N on X. So, okay, so we've got a smooth projective variety. We've got a vector bundle of rank N on X. And now I can form the full flag variety associated to this vector bundle. And so what is it parameterizing? Full flags of subbundles. And maybe as an example, what you really want to think about is just for, if you want to recover the usual situation. So if you take X to just be a point, and then E to just be a dim n vector space, then this is just the usual flag variety of a full flag variety of flags of my vector space. And so here is kind of a relative notion of this. And so we'll be able to formulate Borel-Weil-Bott in this situation. If you want to get back to the original one, we take X to be a point. And then so what is this about? Yeah. If you have a curve, okay, so you have a curve. So let's say, which curve do you want it to be? Okay, so, okay, maybe. Well, okay, so let's say maybe the easiest case. So X is P1. And then, so then what's your favorite vector bundle on X? That's not a, okay, maybe I take it to be O plus the O of 1 here. And so now I'm looking for, so this is rank 2, so I want a rank 1 subbundle of this. So for example, something that would be inside the flag variety would be, well, O of 1 is a subbundle of E. So that would be something. I've also got O is a subbundle of E. So that would be giving a different point inside of this thing here. Yeah, yeah, yeah. Yeah, with a vector bundle. So maybe that's so that's one. Another, maybe a more interesting example would be X. This is an elliptic curve. And so what could I do? Well, I can form, there is a unique extension, non-trivial extension here. And so I could ask both flags of this thing. You know, this is this rank 2 Atia bundle here. And so, okay, then this one would give a point here. And so, but there I have other vector bundles as well. So I can do this for any smooth projective variety, probably even do it without it smooth, and any vector bundle on it. So it's a relative version of the usual flag construction. That makes sense? And so what is BWB about? So it's going to be about pushing forward line bundles on this flag variety. It comes with a structure map back down to X. So it's going to be about, in particular, the higher push forwards of my line bundle on X along this structure map here, which we, by abusive notation, I give it the same map, H. So again, if we want to think about what happens in kind of probably the case of most interest, so then this is asking about if X is a point, then we're asking about the cohomology of line bundles on the flag variety. But okay, so from like this more general standpoint, you're really asking about this thing here. And phrasing it in this type of language has certain benefits, allows us to kind of see where a lot of interesting vector bundles are coming on the partial flag variety and on the Grassmannians. So this is kind of the benefit of this, and then this will help us compute the cohomology of some interesting vector bundles. Any questions? Any questions so far? Borel-Weil-Bott. Yeah, this is a Borel-Weil-Bott. What's it about? It's going to be about these things here.
Can you print out the names?
I can, yes.
So do you, Mike told me this once, but do you remember why naming goes that way? It's something like Borel discovers it's independently first or something, but I don't remember.
Yeah, I think that there was Borel-Weil, and then Bott is came later. And so bot is kind of the harder part. It's only in characteristic 0. And well, there's versions in characteristic P, but the most complete version is in characteristic 0. So for example, if you look at this, some people would call everything we're describing Bott's theorem. Right, so maybe this is really Bott. Okay. So it's supposed to be a statement about these higher push forwards or these cohomology of line bundles. But to do that, we want to describe all the line bundles on the flag variety. Okay, so what can I do? How do I want to say this? Well, so just like in the normal case, or in the kind of the most well-known case we're probably familiar with, that the flag variety comes with a bunch of tautological vector bundles, like the tautological vector bundles on the graph.
Well, that's bad.
Okay, okay. Is this hearable? Is this hearable?
Yeah, I can hear you still.
Okay, perfect. So what are the vector bundles on here? So or the line bundles on here. Okay, so to set it up, that this so sitting on the flag variety, there is a sequence of sub-bundles that give a full flag of the pullback of this bundle here, which is saying that, and so what's the flag that you get given to a point? Well, if you have a point on here, get a map into here from your variety X, and then you pull back this flag here, and then this is the flag that you get. This is the flag that you get associated to a point. So these come, so this is rank 1, this is rank 2, this is rank 3, this is rank n-1, this is rank n. So what I can do is I can produce line bundles on here by setting, let's say Li is Ri mod Ri minus 1. So this is our vector bundle of rank 1. So this is a line bundle. And essentially, every line bundle on the flag variety, on the full flag variety, is built out of these ones. Oh, you are here. Oh, you were just upstairs? Just odd. Oh, you were just late. Oh, I came in on a call. Okay, thank you so much. So we have these line bundles upstairs. And then of course, you know, since I'm in this relative situation, there could be some line bundles on here that I could pull back here. But we're interested in these new line bundles. So we'll call alpha and z to the n a weight. And we'll define L of alpha to be this line bundle here.
Right, we have another mic. Right,
Okay,
okay, finish right.
okay, and maybe I will,
Yeah, just lay it down,
don't destroy it.
hopefully.
Maybe I'll. You be careful of that chair. So from a weight, I build a new line button. There is a green light. Okay. Here. So the point being is that every weight gives me a line bundle, and then these describe essentially all the line bundles on the full flag variety. So these are the things I want to compute the cohomology of. So every line bundle, so maybe here's the, I guess, lemma. Every,
The card group of that space is N.
well, it is really going to be z to the n minus 1 tensored with anything coming from the base. Right, so you're getting n minus 1 new line bundles plus things coming from the base. And I'll just note that, if I took alpha to be all 1, 1, 1, 1, 1, then that would also be coming from the base, because that would be the determinant of my original vector bundle using this filtration here. But the point is that, okay, I can't really say anything in this setup about that the line bundles here have whatever cohomology they do, or if it was a point, there would be no line bundles here. So just these ones here are the interesting line bundles, these L of alphas. And so this is what the BWB is about. It's about computing really these things here. So that's the strategy. We would like to compute the higher push forwards of these bundles L alpha. That's the goal. That's the goal. And so that's kind of that's the setup. That's the setup. So we want to get our hands on what happens when I push forward these new line bundles back down to the base variety, which is the same as computing the cohomology of all of these line bundles here on the flag variety in the special case that X was a point. Okay, I'll just note, so how would you prove something like this? You start off by doing an induction by, forgetting if I wanted to start off with just the full thing, maybe I just forget the first one and I map down to there, and then I try and do induct, and then I forget the second one, and I do like this sequence of push forwards, and then my induction, I kind of get this at every different stage. So one of the benefits of kind of phrasing it like this is that a lot of kind of inductive arguments begin to appear. And the point is that if I forget one of these things, then the full flag variety is a projective bundle over the one when I got the next one. So this allows me to build the Picard group up in steps. Okay. So we want to phrase all this in terms of these weight vectors. So to do this, I'm going to define a shifted action of on these weights. So to do that, let's take rho, could be n minus 1, n minus 2, 1, 0. So this is maybe countdown vector, blast off vector. I've heard it called various things, but okay, we're going to do this. It's the, if you like, more algebraic group stuff, reductive groups. So here we've got this sum of the half weights, but okay, we don't need to know anything about that. We just define it like this. And now if I take sigma in the symmetric group on n letters, I have a natural action on the weights, but I'm going to define a new action called this dot action. So sigma dot alpha, what's it going to be? It's going to be sigma applied to alpha plus rho, this thing here, and then I subtract off rho. So I translate it, I apply sigma, and then I untranslate it. And so now I have this dotted action on, so we have this dot action of Sn acting on the weights. And so this type of formulation is what we need to kind of say something about, or to state BWB. So I'm following Wyman's treatment of this in his book, Syzygies of Vector Bundles. So he calls it Bott's theorem. So if we can find sigma in Sn, not the identity, such that sigma bullet alpha is equal to alpha, so you have a fixed point under this dotted action, then all these higher push forwards equal to 0 for all I greater than or equal to 0. So in particular, if we're thinking about this, or maybe did I erase it? If we're thinking about this in terms of the cohomology, in the case of a point, if I have this, then all the higher cohomology vanishes for that line.
Quantifiers in alpha?
Hmm?
What are the quantifiers in alpha? Is this for all alpha? or some
No,
alpha?
this is for a fixed alpha. Thank you. Alpha is some weight in Z to the n. So I fixed alpha, so I fixed my line bundle. And that if this happens for this line bundle, then I have all the higher push forwards are automatically 0. In the point case, all the cohomology is all 0, no global sections, no H1, etc. Otherwise, so if one does not happen, if it is not a fixed point, then there is a unique sigma in Sn such that sigma bullet alpha equals beta, where beta is non-increasing, then, well, I guess let's put it here. It's two statements. Then we can compute what this is. So this here, this is so beta was non-increasing, so it corresponds to a partition. So every partition gives you a Schur functor. So what is that? That is saying, so given a partition, I get an irreducible representation of GLN. Okay, now I construct the vector bundle whose fibers are that irreducible representation of GLN, doing this patch by patch locally. And that is the Schur functor associated to this partition. So it's the Schur functor of the dual vector bundle here. Yeah.
Say that like you can do this if exists such vector, or every time that you are not in case one will exist such.
So if it's not a fixed point, then there exists a unique. Yeah. So these two cases are mutually exclusive cases, and one of them always occurs. Either one occurs, or if it does not, then there is this unique one here, and this computes what this push forward is, and this here is the length of sigma. So you have this, and then let's say Rj and for everything that's not the length of sigma, then the high push forward is 0. So what does this say in the case maybe that we like the most? So X is a point, epsilon is a vector space, dim n. So then 1 sigma bullet alpha equals alpha. Sigma not the identity. And this is saying that HI on the full flag variety of V of this vector bundle, L alpha is 0 for all I greater than or equal to 0, 2, I find this unique sigma, and then what do I get? I get that h of the length of the flag of the L alpha is now this KB applied to V dual here. So it computes, so it actually does a few things. It computes what this is just as a vector space, but it also computes what the representation of the representation that you're getting when you take the cohomology. That's going to come with an action of a GLV on it, so it's also a GLV representation. And then HJ of the flag variety and L alpha equals 0 for J not equal to the length of sigma. So what it allows you to do is it allows you to compute the cohomology of these vector bundles. So there are combinatorial formulas from the partition. You can see what the dimension of this space is, for example. Maybe not simple formulas. Yeah. No, I think because there could be, if you just gave me a partition, there could be multiple different alphas, right? That were non-partitions that you could dot to get to. Does every partition arise this way?
That must be true. You don't put this action, right? So you, I guess, add row, take the inverse of sigma for any sigma. And then you would get a bunch of candidates for what alpha would be.
Yeah, yeah. So maybe just kind of see like, so how does this actually work in practice? You know, maybe let's take alpha to be, what did I say it was? 3, 2, 5, 1. So here is some weight. Okay, now I can, so here, n is equal to 4. Okay, I could take x to be a point or not, because the combinatorics here is happening, or the dot action is happening. It doesn't really see anything with x. But so let's take this. So what could I do? Let's try sigma 2. I'll say this is the transposition 2, 3. So what is sigma bullet of, let's say, 3, 2, 5, 1? So what do I have to do? I have to add it. So I'm adding 3, 2, 1, 0. So this is equal to, let's say this is sigma 2 of 6, 4, 6, 1 minus 3, 2, 1, 0. Okay, so I'm exchanging 2 and 3. So what is this equal to? So I'm exchanging 2, 2 and 3. So now this is 6, 6, 4, 1 minus 3, 2, 1, 0. And so what do I get? Okay. Now I've got 3, 4, 3, 1. Okay, so I just did this, and so this doesn't really tell me anything, but the idea is I imagine I add this to this and I start trying to do something where I start trying to move these over and kind of put them, I'm trying to start putting them in increasing position. And the idea is you can try and do this with transpositions. Okay, so I got here, and now I should maybe try and move this one over. Let me just leave this here. So if I'm going to try and move this one over, maybe I should apply sigma 1. Leave this here. Yeah. Yeah, it is not increasing, right? I'm imagining, okay, but I'm imagining I would compose two different transpositions now.
So you're trying to get this. So I guess we're presuming that there isn't, it's not a fixed point, or maybe it will reveal itself to be a fixed point. But we're trying to find permutation where the result is.
So what now if let's say, yeah.
This is not, this is neither increasing nor.
Yeah, it's
This doesn't count for phase two.
yeah, it doesn't count for either of them yet. It doesn't count for either of them yet. But what I'm trying to do is try to move it closer to one of those cases.
So maybe when you say, can you clarify that not increasing?
I guess he means weakly decreasing.
Yeah. It's a partition. Yeah, exactly. So I did one transposition, but I could have taken I could have composed two different transpositions. So if I did sigma bullet of what did I have here? I had 3, 4, 3, 1. Okay, so 3, 2, 1, 0. So this is, let's say, sigma 1, 1, 2. So this is 1, 2 applied to 6, 6, 4, 1 minus 3, 2, 1, 0. Okay, but now it didn't do anything here. So now what is this equal to? So now this becomes 3, 4, 3, what is it? 3, but then 3, 1. 3, 4, 3, 1. So what did we get? So what is it saying that if I took sigma 1 bullet composed with sigma 2 bullet of the original one, what was it? 3, 2, 5, 1. Now it is a fixed point. So by composing it, so this one actually was a fixed point. So now, so just saying that HI of the flag is always 0.
Sigma 1, sigma 1 again.
Well, I'm doing sigma 2, then sigma, then I'm doing sigma 1.
But then alpha. Yeah, you mean that sigma 1 of alpha is a fixed point? Or sorry, sigma 2 of alpha is a fixed point. But alpha is not a fixed point. But like you can, if you do sigma 1 again. You want to find something that fixes alpha, right?
Yeah, alpha is not the fixed point.
Yeah, the fixed point is sigma 2 of 3251. I think it, okay, maybe I made a,
Yeah, I think what Keller was saying is that if you go one step further, you'll find the thing that fixes the original alpha, but we haven't found it yet.
Yes, sigma one, sigma two. That thing.
yeah,
Well, except it's the bullet action, and the
Oh,
bullet
yeah.
action is not clear that sigma 2 is its own inverse. Is it?
yeah, I think so.
Okay.
I guess, okay, so maybe I should have said this. So the point is so like this operation that I've done here, so this is called Bott's algorithm. What he says is you start looking at the different transpositions, so sigma I plus 1. And then if you can find a sequence of these transpositions so that repeating it, applying it like this, you end up getting a fixed point, then it is a fixed point. So that, I guess, maybe that is what we've done here. And the idea is, again, like we're trying to get it by taking something here. Why did I pick sigma 2? Well, I took this biggest one here and I tried to move it back this way here. Okay, I didn't get a fixed point yet. But then I looked here and then I had a 4. This was the biggest one, and then I tried to shift it over here to 1. So I used sigma 1, and then if I try and do this, well, then I get this fixed point. And so that this is going to have the non-vanishing, this has the vanishing cohomology. Maybe I'll just write that down. I think I did this. So what is sigma I bullet of, what did I write it here? Okay, let's say this is alpha 1 all the way up to alpha n. So what is the shifting action doing? Well, it only affects, it goes all the way up to what, alpha I minus 1. And then what does it do? You get alpha I plus 1 minus 1, and then alpha I minus 1, and then alpha I plus 1. All the way up to alpha n. So in the ith position, alpha I plus 1 appears, so you subtract 1, and then alpha I that was here goes over here with added 1. And that's what was happening here at these two stages here. And so what's the point? Let's call this star. So this is not a partition. Start trying to make it a partition. By shifting things that are too large further to the right, to the left. And take the biggest thing, start trying to move it to the left. And then two things can happen. So one, you start doing this, and at some point, what could happen? Well, alpha I plus 1 is equal to alpha I plus 1. That was, so here, that was this situation here. So then this is the fixed point case. So you can't ever hope to make it a partition, because at some point you get to this place here where you have this. So if you shifted it, you would get a repeated entry. And then two, otherwise, what are you really doing? You're really just finding the length of this, you're just finding the length of the part, you're finding the length of the permutation that will change your thing into a partition, right? So, and then two, otherwise you find sigma bullet of alpha equals beta. This is the partition. So this is kind of his idea of how you actually kind of do this. You start applying these transpositions and you try and turn it into a, partition. And then you, in doing so, you calculate the length.
So what if alpha has negative entries?
So what if alpha has negative entries? Well, this all still makes sense in that case. So you just go and
You
do
still
that.
just try and order that, like,
Yeah, exactly. It's still just a list of, n different numbers, and you try and make, okay, I shouldn't say partition. I should just say, non-increasing. Yes, yeah. Yeah, thank you. Yeah, weekly decreasing. That makes sense. Any questions? So this is kind of how you do these. This is kind of how you do these computations. You take this alpha, and then you apply, this operation, and then you begin searching for these partitions or these non-partitions to compute the cohomology. Maybe what I'll just say now is, okay, so this is the flag, this is the flag case. So this is the flag variety case here. But we also would like to be able to do this on something like a partial flag. And so let me just describe what that is. And maybe, okay, maybe this is just the, and then this is maybe just the application. So let's take X to be this point, okay, and then so now this is V. So I can compute the higher cohomology on V. Okay. But maybe I want to be able to say something about vector bundles on use this to get some information about things on this partial flag variety. So this is the partial flag variety with the flags of of a dimension D1, D2, D3, all the way up to some DR. Okay, so I have this partial flag variety, and now I'll note that I have a map from the full flag variety of V to the partial flag variety of V. Let's call this H prime here. What is the map? I just forget all the non-relevant flags here. So I can take my L alpha here and I can push it forward to some vector bundle on here. And I would like to be able to say what vector bundle is that. And again, I guess I'm over time now.
Maybe.
Yeah, okay. So the point is that from this relative setup here, by applying, Borel-Weil-Bott to this map, and then the composition of this map down to my original point, it allows me to actually compute explicitly what this is, and then to compute explicitly what the higher push forwards of this vector bundle here. And so we call this vector bundle here, let's say, V alpha. These push forwards are precisely the GLV equivariant, simple equivariant vector bundles on here. So they all arise from pushing forward line bundles in the full flag variety. So you construct a whole bunch of interesting, no longer line bundles, but higher rank vector bundles on here. You can compute exactly what they are using this relative setup. And then you can compute their cohomology by applying Borel-Weil-Bott again. So that's kind of the one benefit of setting it up in this relative formulation. That in fact is also computing the cohomologies of all of the equivariant simple vector bundles on partial flag varieties, more generally on, rational homogeneous spaces, because you can do this, for G mod P, G anything reductive, P a parabolic subgroup. Okay, sorry for going over time.
Let's thank Brett.